So what I'll start with is a quick review of where we were on Monday. I'll define again what stereoisomerism is, because that's what Chapter 5 is all about. My aim is to get through this through Friday, and then next Monday, everything changes. Next Monday, enjoy this weekend. Enjoy this weekend, because it's the last weekend before mechanism. In mechanism, everything changes. Your lives are irrevocably changed. Okay? You'll see what happens on Monday. So enjoy the straightforward stuff while we can, and then we'll get into the more difficult stuff next week. We're finishing up this idea that stereoisomerism is an important idea that opens up the playing field in organic chemistry. You can get many, many more compounds now simply by changing what we call the configuration. Right? That's a big word. And we should point this out, actually. Chapter 4 was all about conformation. Conformation is basically standing up or sitting down. It is basically an energy relationship between things that are more stable and things that are less stable. What we're talking about in Chapter 6 now is going to be, Chapter 5, is something called configuration. And configuration is an identity. And typically you cannot change from one configuration to the other. You can't change from cis to trans. You can't change from what we'll call today R to S. They are stuck in a set configuration. So there's a fundamental difference. And what we started off with on Monday was thinking about where we've come from with this idea of constitutional isomers, how you put the Lego bricks together to make bigger molecules and to put them together different ways so that you can get lots of different compounds from the same pieces. Methoxymethane right there and ethanol are examples of that. And those are two functional groups that we'll be spending a lot of time on in the next couple of weeks. The Chapter 4 was all about this idea of cis and trans on a cycle. The whole point there was the cycle cannot rotate or else you break the bonds. And so you get this phenomenon of the possibility of orientation in the same direction, orientation in opposite directions, and they will fundamentally be different. And if you did well on that part of the exam, you'd recognize that there's a definite difference in relationships in terms of energy, whether something's equatorial, whether something's axial, whether it's up or down relative to something else. So what we do in Chapter 6 is we talk about translating that into sp3 carbon, where you do maybe have some rotation possible, but these things are stuck. They are in a set configuration which cannot change into the other. So you have these isomeric partners. The idea of chirality, handedness, your hands are the simplest example of this, where you put them together, they match across a mirror plane, but you try and put one on top of the other, they're not going to match. You should be able to do that. We can see now that organic molecules can exhibit this idea simply by swapping two of the atoms on an sp3 carbon. If you want to do this in the office, I've got models there. We did it in restation. On Monday, we'll do it again today, where we build the models and prove that this is all about what's called asymmetry. So these molecules do not have any symmetry, and therefore they are asymmetric. This idea from the textbook is a nice one to see where this comes from. If you pick up the glasses on the top right, they should overlap everything on the left. That is superimposable. Down at the bottom, you'll get a mismatch. The idea of non-superimposability, that's what defines an asymmetric center right here. So we now have a setup that opens up the world, because an awful lot of compounds can have a partner, which is the mirror image, but it's not the same molecule, because you cannot superimpose it. You cannot put one on top of the other. So they are definitely different. We're going to call them enantiomeric pairs. We're going to call the two pieces enantiomers based on this idea. So what we need to do today is to expand off of this once we understand symmetry versus asymmetry. And this needs to be quick. You cannot delve on, you cannot sort of spend too much time on this on an exam, because you have other things to do. These are usually nomenclature type points. Later on there'll be mechanistic type points. You need to have this fundamental idea so you can start to play the game. So are any of those molecules symmetrical? No. If you don't say no, then ask, right? If you don't see it, then ask. In other words, over here, the right is not the same as the left is not the same as the right over here is not the same as the left. They have asymmetric carbons. The molecule overall, globally, is said to be asymmetric. So we have this criterion. If we have 4 different atoms or groups attached to a carbon, an sp3 carbon, it may exhibit this idea of chirality and asymmetry. So we can see examples here. We'll get more of these in recitation again. This one over here, symmetrical or unsymmetrical? Symmetrical. We can slice it through the middle. Turn it on its end, as you would. You can slice through the middle. The left matches the right. Down here, we break the symmetry by putting that double bond in there. That is a chiral carbon. Okay? That carbon there is definitely chiral. That is an asymmetric center. This molecule will exhibit chirality. We'll talk today about some of their properties related to each other, and this becomes fairly important. Now, people got stuck on this one on Monday. Is that a chiral center or not? No, it is not. It has 2 methyl groups attached, so it does not fit that criterion, and therefore is not going to be a chiral center. Down here, yes. Over here, yes. These are fairly simple molecules. We started off the chapter by putting some big biological molecules, pharmaceutical molecules up there. That's what you expect to be able to see, right? You should be able to handle those by the next week or so. The relationships between these molecules become obvious if you practice, if you build the models. If you don't have the model kit, come and talk, because I've got lots of them. We can practice that. Enantiomers now are non-superimposable mirror images. We can see here amphetamine. That's just the name of the compound. Okay, that's amphetamine. And if we pick this thing up and turn it around to try and put it on top of that one, some of the things might match, some of the things won't. Right? You can't do this. They're non-superimposable mirror images, therefore they are said to be enantiomers. So we might use terms like this. This is an enantiomeric pair. This is the enantiomer of that. They are enantiomeric partners. Okay? Their relationship is they are the same through a mirror image plane, but they are not superimposable. Different ways of looking at this from the textbook. Practice. The problem here is you're being asked to do maybe something you haven't done before, which is translate 3D information from a flat piece of paper in your head to 3D and back into a flat piece of paper. That's not easy. That is quite tricky. Takes time, takes practice, and confidence. We talked about this idea of why this is important. We talked a little bit about thalidomide and the consequences there. And what we really left off with was talking about how to differentiate one from the other. We can't simply say left-handed and right-handed. It just doesn't work. It's too clumsy. So we need an abbreviation here to be able to talk about the names of these compounds in a confident way, in a consistent way. First off, we should be happy with the fact that these two things are not the same molecule. They are non-superimposable mirror images. If I turn this molecule over and try and superimpose it on that one, it won't work. It won't match. So they have the same requirements, or they have the same bits and pieces and the same connectivity, if you like, but one of those, or two of those atoms or groups are pointing in different orientations. So we'll start talking about something called a prioritization scheme. This is the Kahn-Ingold-Prelog set of rules. You'll use this in chapter 5. You'll use it later on in chapter 8 for alkenes. It's very straightforward once you get the rules. But get it right first time. Don't make up your own rules. Save that for graduate school. In this example, we're looking now at a prioritization scheme based on atomic number. So if you don't know your atomic numbers, on an exam you always have the periodic table on the front page. Yeah? Some of these are obvious, some of them are not, but you always have that there to be able to do this. We'll see very quickly that hydrogen has the lowest atomic number, so we'll give it the lowest priority, number 4. Chlorine here has the highest atomic number, so therefore the prioritization is number 1. And then we have to decide, okay, oxygen has a higher atomic number than carbon, so therefore 2 and 3. Now, we'll start off doing this quite simply, and then we'll build up some complex molecules. We are looking at the atom directly attached to the chiral center. So when you look at these problems, you first of all identify the chiral carbon, and then you look for the atoms directly attached, not groups. If you start looking for groups, you get lost. You're looking for atoms directly attached. So in this case, H, Cl, O, and carbon. And it's fairly easy in that example to be able to break this down into a prioritization scheme because they're all different. Okay, Tyler? Okay. So this becomes a method to get this right every time, so that if you're asking for a chemical, you get the right chemical. You can think now about how this needs to work. In this example, they've started off in a more difficult way than maybe they should. They've got number 4 pointing out of the page. And the rule says once you've done your priority scheme, you should look at this molecule as if number 4 was going away from you. Number 4 has to go away from you. So whatever you define as 4 has to be pointing away from you. Now, we did this in recitation on Monday, and we gave you some hints as to how to get around this. We'll do the same thing in recitation this afternoon to speed things up. What you have to be doing here is imagining yourself looking at the molecule from different angles, from the front, from the back, from the top or the bottom, some of which we did in chapter 4. And most of you are okay with that when we started looking down the bond axes in, let's say, a Newman depiction, or when we looked at the relationships in a cyclohexane ring. Most of you can do that. This is just a step up from there. What you are technically being asked to do here is orientate the lowest priority atom or group away from you. So where it was a wedge here, you should be looking at the molecule as if it were a dash. Simply that means a rotation in 180 degrees. If you need to do that, do it. If you need to do that as you're learning, do it. Maybe later on as we practice and you see some of the tricks we can play here, you don't need to do that. All right, but as you start out, make sure you do this. So what we've got here is a carbon in which number 4 is pointing back. And if I'm looking at this thing like a Newman depiction, I should be looking from there down that bond axis. And if I do that, I should see a Newman depiction. And a Newman depiction might look like this, where number 1 is up, number 2 is left, number 3 is right. Where's number 4? It's at the back. I can't see it. That was the point of the Newman depiction. I don't need to see it because I've followed my rules. I know it's there. I don't need to worry about it. Now, what's the orientation of this? Is it going counterclockwise or clockwise, going from 1 to 2 to 3? Are we all okay with that? Yeah, the iPhone is kind of destroying this idea where you just look at it and it's just a digital number, right? But we understand clockwise versus counterclockwise. This is going in the opposite direction, right? It's going counterclockwise. Now, that will mean something in a minute. When we talk about clockwise, we'll call it the R isomer. When we talk about counterclockwise, we'll call it the S isomer. So we have a designation. The history behind this is kind of fun because R comes from the Latin word for correct, which means rectus. If you think about the vast majority of people are right-handed, and in the Middle Ages, people thought people who were left-handed were weird. I don't know. Some of them are, right? Most of them are not. But people who are right-handed said, okay, correct, rectus, right-handed, that's normal. And then left-handed, different, weird, sinister. And this comes from the Latin word for weird or sinister, sinestra. That's where the designations come from for this type of idea. But it does again relate to left-handed and right-handed, so you have a link between those two things. So in this case, I'm going to do plenty of these examples, and you're going to practice this really, really intensely, is that this is going clockwise, so that isomer, whatever it happens to be, is the S isomer. Its definition now is that it's an S enantiomer, and the enantiomer of it, the non-superimposable mirror image, would be the R enantiomer. So we have some way, like cis and trans, to be able to differentiate one and the other. Again, on my next exam, 4 weeks away, R and S will be on there. A lot of it, some of these low 30% points for everybody who should be able to get these things. That's the type of thing, looking at nomenclature, looking at asking questions. Give me the R and S identification. So you absolutely have to be able to do this, right? If you don't, you're just wasting your time. So I have an example here where we're extending this. We're now in a situation where, okay, there's my chiral carbon. That's the first thing I do is identify it and circle it. And then I ask the question, what is directly attached? And you've got to be careful here because everybody will say OH, IO. And that's not going to happen. That doesn't work like that because it's not the OH that's directly attached. What is directly attached? The oxygen. And then here hydrogen, but here I have carbon, and here I have carbon. So in most of the examples you will see, you have to go a step further. It won't always be, and certainly in my class it won't be, just 4 straight off different things. You'll have to work at this. So I can work out very quickly that O should be number 1 and H should be number 4 based on atomic numbers, but now I have this problem where this is a carbon and this is a carbon. And I want to try and prove to you today that you have to do this systematically, you have to be careful, take your time doing it as you're learning it, or else you can go wrong very quickly. So what we need to have here is some way of breaking this up, some way of deciding which carbon is worth more than the other carbon. And what we need to do is to ask the question, I need to go further. What is attached further away? If I get to a place where they're the same atom, I need to then ask the question, what is attached to those atoms? Because I'm working my way further away from the chiral center, listen to this, to get to a point of difference. Once you get to a point of difference, which we'll lay out in this format at the bottom, you can then make a decision which is more significant than the other. So down here, what we're asking here is what is directly attached to this carbon? We're not counting that carbon because we already did that. We're working our way out. So what is attached down here is a carbon, a hydrogen, and a hydrogen, labeled as such. And I'll teach you, and I think it's in the textbook the same way, you lay it out like this in parentheses, just to keep yourself organized, because as you get more complicated here with many stereocenters in one molecule, you can get lost very quickly. You can get overwhelmed very quickly here. You take your time, it's not so bad. So what I've done here is translated CHH here into my little device like that, CHH. And I put the highest atomic number first. If I put the highest atomic number first, this will help me work out which is more important. Now, if I look at this example here, this also happens to be CHH. That's not so good because they're both the same. Left is the same as the right. What do I need to do? Go further. And in some of these molecules, you have to go far. You have to go 3, 4, 5 atoms away. And you just take your time with it, and it works every time. So if I keep going, I'm done with this carbon. I'm asking here this carbon and this carbon. Now, what's attached over there? CCH. And what's attached over here? CHH. And that's all you need to do. So which is more significant, left or right? Left. That would be number 2. This would be number 3. Do this in pencil. And have one of those really useful little devices at the end of that pencil that allows you to erase what you just did in case you get lost. Okay? Just take your time, and there's nothing too difficult. So we've got some basic rules. You've got to prioritize your atoms or groups based on atomic number. If you get to the point where they're the same on either side, go further, as far as you have to do to get to a point of difference, and then label them 1, 2, 3, 4, and then orientate the molecule in the right direction so that you can decide how to look at the orientation. So here we had the tiebreaker. That was CCH. Again, I'll write it in the format I like and keep it simple. And over here it turned out to be CHH. And because of that second letter right there, carbon, this is higher priority than the one on the right. That's part of the job. And I tell you this, if you want to do this quickly and do this well, getting ready for an exam, you need to do these things in about 30 seconds. right? That's the goal. If you struggle with these things, you ask very quickly. So now we can move on. We can think about situations in which we've got different atoms involved, not just carbons. So if I go to this situation, I have a carbon right there, which is asymmetric. That is a chiral center. And I think about now what is it directly attached. The O and the H, I don't care about this hydrogen because I've already gotten what I need from that piece without going that far. Down here, I've got carbon and I've got carbon. So I have to go further. You've got to be careful here, because if you lay this out, what is attached on that carbon are 3 carbons. C, C, C. Absolutely. And attached over here is O, H, H. Not this H, but the 2 hydrogens that are bonded there. Now you set this up properly, you set this up appropriately so that your highest atomic number goes first. You have a point of difference. You have the tiebreaker. This beats this. Yeah? You don't care about this. You don't have to worry about those because you already broke the tie. So now I can put in my numbers again. Number 2 would be over here, and number 3 would be over there. Setting this up is fairly simple, but after you set it up, you then have to look at this thing and analyze it to get the outcome, to get the right answer. Everybody okay? Anybody want to say anything? Anybody here? No idea what your name is. Go on. What's the name? Kelsey, go on. Yes, we're going to build up to that. We're just showing you how to set up the initial view of the thing. So you get 1, 2, 3, 4 organized. Some little rules that allow you to differentiate very quickly what is 1, 2, and 3, and 4. And then we'll build into a load of examples. Ashley, you okay? Haldeman. If this didn't have the OH group, then this would win on the right-hand side. Yeah, and you are going to practice so many examples. I'm not asking you, I'm telling you. You're going to practice so many examples, you will be an expert at this. Okay? Fair enough? Deal? Right, good. I will call you on that. Now, there are some extras here, because you can imagine the complexity of organic molecules. You're going to get to some point where you start scratching your head. I haven't seen this before. Well, we do the simple rules. We keep it simple. There's a document on my website that lays this all out for every single example you can think of. It's a great detail thing, but we'll just deal with the basics. Well, if I think about this carbon here, I think, from my view, remembering when I struggled with this myself, that molecule is fairly complicated now, because I've got carbons coming off. I don't have any functional groups necessarily on that carbon. I've got carbon sticking off, got hydrogen sticking off. That, to me, makes it more complicated. But that is indeed a chiral carbon, because that's a CH3, that's a CH2, CH3, and that looks like a butyl chain. And then I have an aldehyde sticking off at the end. So I can now think about this in terms of prioritization. It's going to be fairly obvious that, okay, everything is carbon here. And as I build this up, I've got to take my time and decide what else comes next. If I think about the carbons, what's attached to this carbon at the bottom if I were to write my list? HHH. When you get good at this, it's great. You just fly at it. It really is straightforward once you see it, but it's up to you to put the time in to get there. What is up here? If I've hit my carbon there, and I'm thinking about what comes next, what is it? CHH. And if I keep doing this, and I go to here, what's there? CHH. So you see how it's building on stuff we did in the first couple of weeks? You have to understand these skeleton structures to be able to know how many carbons and hydrogens are there to be able to define these things. It's getting more complicated. Well, that doesn't help me much, right? Because CHH and CHH are the same, so I need to go further. I need to go here and here. And what's attached up there? HHH. Okay? I'm working away, so HHH. What about this down here? What's attached there? CHH. So now I have a point of difference for those groups. So I can work the same way I've just done with the simple examples for that part of the molecule. That's not a problem. Just use the rules and apply them. Well, the issue comes over here, because I don't seem to have an sp3 carbon. I don't seem to have 4 different things attached. But you treat this as if you do. You treat this as if this carbon is bonded twice to oxygen. So double bonds, you count twice, the atom attached. Triple bonds, you count 3 times, the atom attached. That's quite simple, quite easy to remember. Now, if you want to write that out, we would say O, O, H. So O is bonded once, twice, O, O, H for what's left over. And very quickly we have a nice way of differentiating this. Which do you think is number one? The right-hand side of the molecule or one of the alkyl groups? The right-hand side, because my oxygen beats my carbon. So we then have to worry about orientation. We've done a few things so far. We've looked at the molecule, decided if it is chiral, if it contains chiral centers. If not, you don't need to worry about this stuff. But guess what? They will. So then you have to decide about orientation. Identify the chiral carbon, look at the different atoms or groups attached, define them as 1, 2, 3, 4 using these criteria, and then we need to set this thing up to look at it from the right direction to get the R or the S. This, I think, is the hardest part of all of this. So the rule says put number 4 pointing away from you every time, if you can. If it is already pointing away from you, great, just carry on. You're already set. If it isn't pointing away from you, if it's pointing towards you, you have problems. If it isn't pointing anywhere, if it's in the plane of the board or the paper, you have real problems. Because you now have to do what we did with the Newman depictions, which is why we did them, and look at systems and decide, all right, is that to my left or my right? It's on a flat piece of paper, it's on a flat slide on the screen. But is it to my left or my right if I'm looking at this thing as a 3D molecule, using my wedges and dashes as indicators of direction? So now we're taking this 2D world into the 3D world, which is not particularly easy. In this example, 4 is pointing back, so now my thing is counterclockwise. Every time that's the S configuration. And there's that word, configuration. This is not conformation now, which was standing up or sitting down. This is configuration, which is absolute identity. You'll have fun with this. Now, I always try to get an elephant in somewhere. Just off the top of your heads, who thinks the right-hand side is more significant than the left? Because it's got a big, huge elephant right there. No, Johanna, that's right. Because as you work your way across, you know, it's like, oh, cuddly elephant, huge. That's bigger. That must beat this. No, you haven't followed the rules. Because if you work your way across, C, H2, CH2, 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 O, CH2. Before I get to the elephant, O gets in the way. So it turns out this will actually be more significant this side than it will this side. So don't get lost in this. Learn the rules simply, learn them from the ground up, and you'll be fine. And what's bigger than an elephant? 2 elephants? No, a planet. And it's the same deal. Take your time. It's just an exaggerated way to show you that this needs to be done carefully. If I look at the chiral center, it's this one. I might put in my hydrogen to make sure I understand it's there. It happens to be pointing away, which is nice. A lot of them aren't. And I can now deal with what's directly attached. What's number 1? O, not the OH. 1, right? O. What is number 4? This hydrogen. Now I go here, I get carbon. I go here, I get carbon. So I have to lay these things out. What's attached here? CCC. Okay, what's attached here? CCH. So it turns out irrelevant. Yeah, irrelevant. Over here is more important, more significant, higher priority because you've followed the rules. If you do that, it works every time. If you don't, you get lost. So if this is number 2 over here, and that's number 3 over there, what's the configuration, R or S? S. We're going from 1 to 2 to 3. This is already lined up in the correct direction. That is the S enantiomer of cyclohexenol planet, whatever that molecule is. Just don't get lost. Jacob. That's forward a slide. That's back a slide. That's back 2 slides. Oh, you just want to look at the elephant, don't you? I like elephants too. I think elephants are great. I didn't write a 4 by elephant. I wrote a check to start off because I thought my mind went there. It's like, oh, big elephant, that's huge. That must be more important. Then I went, no, that's wrong. That's not a 4. Sorry, elephant. So be careful with this stuff. Be very careful here. It is very easy to get lost if you are not paying attention. Haldeman, how much practice are you going to do? A lot. So here is a scheme. Here is a chart that shows you the steps you have to take to do this. If you want a summary of what we've just done, there it is. Identify the 4 atoms. Decide if you've got a 1, 2, 3, 4 going on. When you start to get to points of the same atomic number, you have to go further away. Once you've got 1, 2, 3, 4 organized, you rotate the molecule. Do you have to rotate the molecule? I suggest if you get this stuff, no, you do not. If you don't get it from the beginning, do so. Turn it. Set it up so you can see it as a Newman depiction so that the smallest The lowest priority is pointing back. I'll show you where that comes in a second. So we can now start to talk about the absolute identity of some of these molecules. There's my hydrogen. What's number 1 on my chiral carbon? What's number 4? What's number 2, left or right? The right, okay? This would be C, HH, this would be HHH. This would be number 2, that would be number 3. What's the orientation? Because the hydrogen is pointing back, it's nicely set up for this. Is it clockwise or anti-clockwise? It's clockwise. That's correct. That's the R enantiomer. Now, I'm going to try and do this here in front of the big class, and we'll do it sort of in smaller groups in recitation, but this is how you can work around one of these problems if it isn't pointing in the right direction. So there's the enantiomer. It's obvious it will be the S isomer because the other one was the R isomer. But we need to see that independently. Same scheme, 1 for the O, 4 for the H, 2 for this thing, 3 for this thing. If you have the time, and if you don't see this, you turn it in space. But the other alternative is you imagine yourself looking from the other direction. You imagine yourself looking from the back of the molecule, because this is pointing in the wrong direction, right? My number 4 is going in the wrong direction. But there are only 2 ways to look at this, front or back. If I'm standing from this side here, what's the orientation? Well, no, that's the configuration. What's the orientation? Is that clockwise or counterclockwise? Right, so I'm standing in the opposite, I'm opposite, right? I see that. What do you see? Some big English idiot waving his hand around. If I see that clockwise, what do you see? Counterclockwise, and counterclockwise is therefore S. That's how you speed this up. If you want a little device to get this done quickly, because it really is setting other things up, this again is a fundamental, simple concept that we need to worry about for more important things in chapter 6 onwards. If you can do it that way, it will speed things up. So if you're looking from the wrong direction, change your orientation. You should be looking the other direction. So we need practice. We need lots of practice, Alderman. Now, I have a molecule here which is now more complicated than where we were. Welcome to organic chemistry. That carbon contains or is attached to 4 different atoms or groups, no doubt. So I can set this up and start doing some practice problems. What's number 1? Br. I have a carbon here, I have a carbon there, and a carbon there. So if I deal with this one first, what do I need to write down to say what's attached? Who said C? I've already dealt with the C. HHH. Okay? If I look at this down over here, what's attached directly, working away from that carbon? CHH. And I need to be over here now. What's attached? Now let's do it in order. OCH. Okay? Basic, some basic idea of what atomic numbers are, and you should know those from the past, so you can do this quickly. So what's number 2? The bottom, the top left, or the right? That's number 2, because of the oxygen. That wins. And what's number 3? The left or the right? Is my number 4 going in the correct direction or the wrong direction? The wrong direction, so I've got to be careful here. What's my rotation so far? Clockwise, like that. I'm doing this, what do you see? Counterclockwise. Erin. To keep the atomic numbers going from higher to lower. Is it OHH? My bad. Yeah, you're right. Okay. But the oxygen goes first to keep it in order. Yeah, so we have that point of difference. So this is fun. Don't let other people see you practicing this stuff. Don't do it in the library. You'll get arrested, right? Do this stuff, do it elsewhere. That's S. Fair enough? Okay, do more. Practice. Is there a chiral carbon in that molecule? Yes, there is. This is it. I have 4 things attached. 3 of them happen to be carbon, 1 of them happen to be hydrogen. What's number 4, obviously? Hydrogen. Now, carbon, carbon, carbon. If I go here and I work my way away from there, what's attached? HHH. Keep it tidy. What's attached down here? C, C, H. Yeah, we see the double bond there, counts twice. And what's attached there? CHH. So even though that molecule looks a bit different, a bit more to it, use the same rules, you get the answer very quickly. What's number 1? Bottom, left, or right? Number 2. Number 3 is all that's left. And my rotation now, rotation is what? Is clockwise or counterclockwise? Clockwise. And it's in the correct direction, so what's the outcome? There's a lot more to it because it's R something. It's R whatever that molecule is, cyclohexene. That's where we go in the next couple of chapters, is building up functional groups, using this designation to be able to tell which is the right outcome. So that's the R isomer. Is there a chiral center? Yes, there it is. Now, what's number 1? This is going to be difficult. Here I have what's attached. What else is here? It's a carbon. What comes next? HHH. Over here is a carbon. What's attached? CHH. And over here, what's attached? CCH. So what's number 1? We already said that oxygen. What's number 2? Left, right, or top? What's number 3? Top. What's number 4? We already said that, or we didn't, but that's number 4. Now, what's the problem with number 4? And this, I think, is the most difficult example when this happens. It's in the plane. It's neither front nor back. Yeah? It's neither front nor back. So you do have to start doing this. You do have to start sort of trying to work out. If you have the models, you can do it without looking weird. You do have to start thinking about 3D. Is this pointing left or right? Is it a wedge or a dash? What does that tell me? So I've got 1 at the top. I seem to have 2 down here, and I seem to have 3 over there. If I'm looking from here, what on earth is that? I don't know. That's an eye. Jacob, that's an eye. Right there. I'm looking down that axis. Is it okay that my OH is sticking up from that angle? Just like it would for a Newman depiction. Yes? Is it okay that my 2 is sticking roughly down? Yeah? Now, what direction is my 3? Is it to my left or my right? To the left. You don't see that, you need to. It's to your left. So if I'm looking down this direction, I can do this because I've orientated or angled myself to a degree that I can see the correct way, down towards number 4. And that looks like it's going clockwise, so what's the outcome? Yeah? See how this works? Chiral or not? Asymmetric center or no? Yes. Anybody see it straight off without thinking about it? What do you see? You see RS. R. 4, 1. This will be 2. This will be 3. Correct direction. Clockwise. R. That's how you speed things up. It's practicing. You get better at it. But check. Don't sort of assume you know what you're doing. Something like this might be a bit tricky. There's my hydrogen in the wrong direction. I might have to look from it from the other angle. I now have 2 oxygens attached. I have an O and an O and a carbon and an H. Number 4 is obvious, yes? Number 4 is the H. Now, number 3 should be obvious because the other 2 are oxygens, and that's carbon. I have to decide now between these 2. I've got an O, they're the same. I've got a C, they're the same. I've got 3 hydrogens, so HHH. What's attached down here? CHH, so that wins. I do the same thing. So I already dealt with 4 and 3. This, I think, is 1. This, I think, is 2. Is that correct? What direction are we pointing in? What rotation do we have? Counterclock. That's not the rotation. That's not it. Just be careful that you don't jump ahead. Am I having counterclockwise or clockwise? It looks like it's going 1 to 2 to 3. But what's the problem with number 4? Wrong direction, so it should be the other way around, right? Don't get cocky with this stuff. Learn it thoroughly so that you don't get lost. I've seen some very good people get very few points on these types of questions because they thought they knew what they were doing and they didn't. Joe? Actually, at this level, we don't care. You take a graduate class on this, you care. Actually. So number 4 is the hydrogen, no doubt. Number 3 is this guy right here, because it's a carbon. The other 2 are oxygens. Down here ends up having more stuff attached than up here because you run out of, you end up with hydrogens. Down here you end up with an extra carbon attached. So that makes that number 1, that number 2. Friday, boy, whoa. Because you'll all know how to do this by Friday. Is there a chiral center in this molecule? Yay or nay? Yes, there is. It's right there. Is this a problematic one or not? Is number 4 going to be a nuisance? Yes, it is, because the CH3 will be number 4. What's number 1? What's number 2? Right, now I have a C and a C. Here I have CHH. Here I have what? HHH. Point of difference. Well, I've got to imagine myself looking down this axis again from, I shall now try and do a better, there we are, pretty. Looking down from there. What's pointing up to my right? Bromine. Do you see that? We're in good shape. What's pointing out to my left? Fluorine. What's pointing straight down? The chain. So if I've decided now that that's number 1, that's number 2, this is 3, and this is 4, what am I looking at for the rotation? Clockwise or counterclockwise? Counterclockwise. Good. From there to there, correct orientation, because we're looking at the molecule in the right order, and that should then be S. Fair enough? Okay, good thing to learn soon. Anybody? You want me to spend as much time on this as possible, because then I don't need to talk about things on Friday, because Friday is woof. I mentioned Monday was the beginning of the end. Well, Friday is the beginning of the end. This big hill we have to go over. So what we can do now is talk about adding different pieces, adding extra chiral carbons. We can start to expand the alphabet. In this case, we seem to have 2 chiral centers as designated by those 2 numbers and letters. We don't know an awful lot about this yet. We will by the next exam. We'll have covered enough functional groups by the next test to be able to use this stuff thoroughly. And we now recognize wedges and dashes really mean something. So we should be able to look at this thing very quickly, recognize the H is in the wrong direction. Sorry, it's in the correct direction. Here it's in the wrong direction. And work out our answers, R and S, very quickly. That's one way of doing this. The other way is to be given the molecule and to work out its name, or given the name and work out its structure. That's much more difficult. That's what's coming up next. So we need to be careful here to understand that chiral compounds are there. They're very important, but they're also a bit of a nuisance to a chemist. We find that if you have the left hand of a molecule and the right hand of the molecule, they're pretty much the same thing, other than this, right? So we find in reality that the melting points of those compounds are the same as each other. The boiling points are the same as each other. Have you done TLC yet in lab? You haven't yet, have you? You will do soon. Chromatography, separation techniques are the same. They have the same properties. They might not have the same taste, because that's because you're introducing them to a chiral environment, your body, which can then tell the difference. But for the most part, we can't tell the difference between the left and the right. We can label them as different names, but we really can't tell the difference, apart from this one technique. It's a bit of physics. You're not going to spend a lot of time on this, but we're going to put our sample into a box. And this is a box that's kind of expensive. I have one in my lab, $20,000. Gives me one number. And when you're trying to persuade YSU to buy you one, it's kind of, what does it tell you? Does it make coffee? What does it do? No, it gives me one number. Okay, how much is it? $20,000? Yeah, right. But we got one eventually, and it's very important that we get that number. So it turns out now this is simply a matter of exposing your sample to what is called plain polarized light. You don't need to know any physics about any physics here. But it turns out that if you put your sample in plain polarized light, if you wear Polaroid sunglasses, that's the same sort of idea. You're just taking out most of the light and you have one direction, one plane. Different samples, depending upon whether it's left or right-handed, bend the light in different directions. It's weird. It's magic. But the R isomer might send it in one direction, and the S isomer sends it in the other direction. And they send it equally in those opposite directions. So that sort of is what it says at the bottom. Enantiomers have equal but opposite rotations. So we can tell the difference between one sample and the next based on the direction of rotation and the angle of rotation. You're not going to do any calculations here. I promise we didn't need calculators for the class, that's true. But you're going to learn what an alpha D tells you, what a rotation tells you, because we can use it later on for mechanism to work out what the outcome was, what the mechanism was. So this idea now is based on the polarimeter. You put light in, you have a polarized sunglasses basically, gets rid of most of the planes of the light, you get one plane of light, it goes through your sample, and if your sample is chiral, this is all you need to know. If your sample is chiral, you will see a rotation away from the zero. Wherever you started out with, the direction of that light, it will bend, left or right. And at the end we have a scale, and we can measure those differences, those deviances from zero, and we have a number. and we will call that an optical rotation. So any molecule that's chiral tends to be optically active. Optically active meaning it has this phenomenon. If you put a sample in this box that isn't chiral, 0, 0, 0 all the way. If you have a chiral molecule, you get a rotation. So that's enough of that. It turns out now we have to have a standardization. You know, maybe my polarimeter in my lab is a certain size. Maybe it's an expensive one. Maybe somebody else has got a, you know, in your basement lab, you've got a polarimeter that's, you know, Walmart version, and it isn't quite so fancy. You need to be able to say the same numbers. Okay, you need to be able to differentiate, you need to be able to define the same numbers. So all specific rotation is taking into account the fact that different people across the planet have different polarimeters, different instruments. That should be fairly obvious. So what we do is we measure the actual angle, whatever that happens to be. It might be different in my lab and your lab. And then we deal with the concentration of the sample. That makes a difference. The more sample you expect, the more deviation. And then the length of the tube. If you're taking a standardized test in the future, you probably need to know that. I don't ever test on that in my exams, but that's what it's about. Standardization of the rotation to give what we call a specific rotation, and that specific rotation gets this symbol. You'll be seeing a lot of alpha D. Alpha D will be your friend. If you haven't got any friends, you have now alpha D. Be nice to it. Alpha, rotation, the square brackets tell you it's a specific rotation that's been standardized. D is the light source that was used, the sodium D line. Right? That's how we generate the light. 20, what temperature you ran the sample at. That's a standard experiment, 20 degrees C. So that will give you a number, and here's what you need to be concerned about. One enantiomer will have the negative rotation, and the other enantiomer will have exactly the opposite rotation. Where one's negative, the other one's positive, but they're the same amount, the same size. Somebody will ask me this question: can you tell whether your molecule is going to be plus or minus? I think you can these days, but we can't. We don't really care about that. The fact that they're opposite is enough. This is for one enantiomer, this is for the other enantiomer. And we'll see later on as we start to use this in mechanism that this piece of information becomes really, really useful. So now what we've done today is go much further in depth. We talked about the idea of how to define an organic molecule that is chiral, how to look for the stereocenters, how to tell whether they're R or S, and now we have a physical measurement to be able to tell them apart. That's the straightforward stuff. What we'll do next, I'm not going to talk about this, right? So just get rid of this. We might later on when we get some mechanisms, but right now it's going to confuse you. So get rid of that for now. What we've done so far has been fairly safe, in the sense that most, if not all, of the molecules I've put up on my slides have had one chiral center. Now in biology, you're going to get many more than that. In glucose, the most important, I would say, or one of the most important biological molecules out there, you have 5 chiral centers. So it's a much more complex system. So we need to have some new definitions to be able to talk about compounds that are more complex. We started off a discussion way back about what isomers are. You put these building bricks together, Lego bricks together in different ways, you can build different isomers. Well, we can talk about constitutional isomers, where you simply change the order of things. Maybe you can have a hydroxyl group instead of an ether. Those things are constitutional isomers, and they're different molecules. What we've done in the past couple of weeks has been stereoisomers, where cis and trans fell into this category, or now R and S fell into this category. And very simply, when you had a system which was the mirror image, we have something called enantiomers. But now we have to deal with this, and this I think is far more complicated. You have to deal with something called a diastereomer. Diastereoisomer, or abbreviated diastereomer. And these things get very complicated. We need to understand that if you've got 2 or more chiral centers, you're not just going to only have enantiomers. You're going to have other molecules related to those compounds that are not their mirror images. Because we're going to see different ways of putting the groups together to give different outcomes which are not the mirror images. So that's where this word will come from. We'll say that diastereomers soon are stereoisomers which are not enantiomers. They're everything else. If you can't define them as enantiomers, they're probably diastereomers. So it's just an extra definition. So we'll start this out. And again, what I like to do is start on something that I think is complicated, then give you a chance to chew it over the next couple of days, and come back and start on this on Friday so that we get it. This is a typical system with 2 stereocenters. And you can see here more possibilities for orientations. We don't simply have left and right-handed anymore. We have 4 possibilities. And usually that's your maximum. So what you want to start doing here is looking for the number of stereocenters, and we'll call it n. And then you do 2 to the n. So 2 to the 2 is 4. I've got 2 stereocenters here, so my maximum number of isomers will be 4. And I think you should be able to see pretty quickly that these 2 are mirror images. And if you turn one up and put it on the other, they won't superimpose. So they're enantiomers by definition. And everybody after today should be able to give me those RS identities. And then over here we have something different. And this takes you a bit further from where we were in chapter 4. In chapter 4, I said in class and in recitation, if you're going to make me a cis isomer, it doesn't matter if you put 2 wedges or 2 dashes. It didn't at that stage. They were still cis isomers. But now we're digging deeper. Within the cis isomers, it does now matter if they're both wedges or both dashes. In the trans isomers, it does now matter which orientation they are, because we're now talking about chirality, which are in those molecules. So here I have 2 that are cis, and here I have 2 that are also cis, but they're no longer the same molecule, because they're opposite. You see here, R is opposite to S, and S is opposite to R. As you practice with the modelers, as you practice naming these things, you'll notice that R mirrors S, and S mirrors R. Even a big molecule, the enantiomers will be the opposite stereocenters. On the right-hand side, earlier on, when we did cyclohexane stuff, we said that that was the same as this, pretty much. They were both trans isomers. Now they're not. Now we can introduce this idea that they're not because of the orientation in space, which makes them stereoisomers within a set of stereoisomers. That make sense? You have cis and trans, which are stereoisomers, and within those stereoisomers, you've got more stereoisomers. How much fun could that be? Marissa? Yeah? It's going to be great, this. I have RRSS. And I'll set this up for Friday, and then I'll break until then. You're always going to get RS and SR. You're always going to get RR and SS. Those are the only 4, and I'll use this word carefully, the only 4 permutations for how you can set this thing up. And you notice consistency. If this is a wedge over here, and it's the R stereocenter, and it's a wedge over here, it should still be the R stereocenter. If this is a dash over here, and it's the, what is it over here? It's the S stereocenter, it should still be the S stereocenter over there. So have a look over the next couple of days, do homework 5, practice these things, and we'll have another go on Friday.